This is the video with the assignment of the Coursera, Duke University, Machine Learning Foundations for Product Managers course. In this project, I built a machine learning model to predict the net electrical energy output of a combined cycle power plant based on environmental conditions. The dataset contains over 9,500 hourly records, and I used 80% for training and 20% for testing. The input features represent ambient conditions measured at the plant: temperature, vacuum, pressure, and humidity. The target variable is P, the net electrical output in megawatts. My goal was to accurately predict this output using those environmental inputs. Since we're predicting a continuous numeric value, I treated this as a regression problem. I chose linear regression as my starting model because it's simple, interpretable, and easy to run in Excel. To evaluate model performance, I used two key metrics: R-squared, which shows how much of the variation in the target is explained by the model. The closer to 1, the better. And RMSE, or root mean squared error, which tells us how far off our predictions are, on average, in megawatts. Lower RMSE means better accuracy. I started by training a linear regression model using all four input variables. The results were strong. An R superscript 2 of 0.929 and an RMSE of 4.53 megawatts, meaning the model explained nearly 93% of the variation in energy output with low average prediction error. Next, I created a correlation matrix to understand how each feature relates to the target variable, P. Temperature, or AT, showed the strongest correlation with P at -0.95, making it the most important feature. To build a simpler model, I looked at which features could pair well with that. AP had a stronger correlation with PE, but also overlapped more with that. RH had a weaker correlation with PE, but was more independent. So I decided to build two simplified models, one using AT and RH, focusing on reduced multicollinearity, and one using AT and AP, focusing on maximizing correlation strength. I tested two simpler models with just two features each. Model 2 used temperature and humidity and explained 92.2% of the energy variation. Model 3 used temperature and pressure and explained 90.1%. Model 2 also had lower prediction error, 4.77 megawatts compared to 5.35. Because of that, I chose Model 2 as the better simplified model. Model 1, which included all four features, had the best performance on the training set, with an R superscript 2 of 0.929 and an RMSE of 4.53 megawatts. Model 2, using only temperature and humidity, had a slightly lower R superscript 2 of 0.922 and a slightly higher RMSE of 4.77. Despite that, I selected Model 2 as the final model because it's simpler, reduces the risk of multicollinearity, and still maintains strong predictive performance. It's a more generalizable and efficient option for future use. This is the final formula from Model 2, which uses temperature and humidity to predict energy output. The coefficients you see were calculated from the training data and then applied to the test set to generate predictions. When tested, the model achieved an R superscript 2 of 0.918 and an RMSE of 4.91 megawatts, very close to the training values. This confirms that the model generalizes well and is not overfitting. Compared to Model 1, the drop in accuracy is minimal, only 1.1% in R superscript 2 and 0.38 megawatts in error, but Model 2 uses fewer features and avoids redundancy. That makes Model 2 the better choice: accurate, efficient, and more reliable for deployment.